That's what I wanted. Okay. So in the video that I asked you to preview before today's class, I went through the first couple slides in this slide set, and it was mainly meant to refamiliarize you with the different varieties of amplitude modulation. So I'm going to assume that you all did the assigned viewing and skip straight to slide number 6, which was the conclusion of the video that I linked you on Friday. And the reason that I want to start here is because today's lecture will start by talking about this column. And so I want to just make sure we're on the same page about what synchronous versus asynchronous detection sounds, or it means. Actually, can anyone offer their interpretation on this? I want to see where the class stands on this. What does it mean when a detection scheme is synchronous versus asynchronous?
I think it being synchronous means that you need an oscillator on the other, like a mix or something on the receiving end, right? And then you don't need that for the pure AM because you just kind of extract the signal from the envelope.
Yeah, exactly right. So that's exactly right. When I think of synchronous detection, I think of two oscillators in synchrony, one at the transmitter, one at the receiver. So that's when I read the word synchronous technique, I envision these two waves in sync, and that always bothered me when I took lower division communications. Like, isn't the whole idea behind wireless is that you don't have to have shared communication between the two? And so I want to spend today talking about how this is actually accomplished, because you've driven a car, you've heard AM radio. Actually, I don't know if both of those statements are true for everyone these days. You have probably heard synchronous detection, and you might not have known how it was done. And so the answer to that comes in the black art, the black magic of phase locked loops, or PLLs for short. So the idea is that this is the architecture on a receiver of some RF system. Okay, so if you like, here is a antenna, and we are getting radio waves impinging on that antenna, and then what we're getting from that antenna can be described by the following constant amplitude sine wave. So if you like, we can just be talking about almost binary AM. So for a single set bit period, we'll talk about a constant amplitude, whether that's positive A or negative A or whatever. We are going to write the incoming wave to our system as being a sine wave, whose argument is strange, right? This is an atypical way of writing the argument to a sine. What I'm saying here is that there is some kind of nominal frequency. But I'm going to allow that the phase can vary as a function of time. Okay, so if theta I of t, I for input, if theta of t is 0 for all time, then we have a fixed sign in the input, and it wiggles at frequency omega c, the carrier frequency. But if we allow for what I envision to be something like a deviation, then all of a sudden we are admitting a larger class of signals into this detector, or this PLL. And so let's kind of skip from beginning to end, and at the other end, the output of our PLL is going to be what we're going to call the cosine at the same nominal frequency. And if everything goes well, we're able to track the phase. So theta O should be equal to theta I. This is the idea. We're tracking phase not necessarily frequency, but that's where the phrase phase locked loops comes from, is that we're trying to lock the output phase onto an input phase. And if this seems like a controls problem, that's kind of why I'm spending today's lecture on it, is because I can't not talk about controls and communications. It's like the two best parts of electrical engineering coming together. Okay, so let's take a little bit of time and understand what else is going on in this loop, this control loop. So VCO stands for voltage controlled oscillator. Voltage controlled oscillator. And if you're not familiar with these things, nominally, it's the idea that if you set, if this is your kind of V in, then this output is like a frequency. Okay, so you would go to the store and you would buy a VCO that had a set quiescent frequency. So that is when 0 volts get applied to it, it oscillates at whatever, 2 gigahertz. And then the other parameter of a VCO, base parameter, would be what slope does it correspond to. So for how many volts in, how many radians per second or how many hertz does the output oscillator vary? Now, so we're just going to talk about linear VCOs or ideal VCOs, but I don't think it'll surprise you to learn that the actual characteristic usually looks something more like this, where there's only a finite usable range beyond which the oscillator won't oscillate any quicker. Okay, but we're gonna restrict our attention to ideal or linear VCOs. Man, this lag is killing me. Okay, so the idea is that we are going to set up something called a phase detector that's going to take 2 inputs, what we're currently outputting and what we're currently seeing as input. It's going to try and measure the phase between those 2 waves, and that signal we're going to send through a filter, and this is what we're going to focus on today, because this is where all the design choice comes into play. So this is what we're going to design. Okay, the output of your loop filter then decides the input to your VCO, which then changes the rate of oscillation, which then changes the output, and then we're back to where we started, go back around the loop. So one way to implement a phase detector, so I'm here in this first block, is to just multiply the 2 inputs. This is kind of like, you'd think a phase detector would have to do a difference, but kind of a cool result is if I multiply VI of t with VO of t, I get this line. So I'm laughing because one of your classmates told me that his 314 experience was 10 weeks of multiplying sinusoids and using trig identities, and he didn't feel like that was a college level class. I think that was his simplification. So I'm sorry, but we are going to use a couple of trig identities here and there, and this is one of them. That if I multiply a sine with a cosine, I get to do this thing to them. The benefit of this is that this has the output, so P of t, is going to have something that varies very quickly. So this is kind of high frequency. And then the assumption is going to be that this term is going to end up being lower in frequency. And so if our loop filter ends up having kind of a low pass type characteristic, then we're going to be able to kind of wave our hands and say, you know what, that doesn't actually get passed through the loop. And so we can focus on the difference here, the lower frequency difference. Any concerns with this? This is a much higher level than I would teach 302, but you've all taken 302, so I'm assuming we're good. Tell me if we're not. I'll only take a little bit of offense. Okay, so the other side of the slide is kind of the characteristic of what an ideal VCO ought to do. So when you are putting together this circuit, you would put it together assuming a fixed carrier frequency. So this would be, I want this PLL to track 2.5 gigahertz. So you go out and you buy a VCO whose quiescent frequency is 2.5 gigahertz. And then this C is the slope that we were talking about up here. So this is for every volt that comes in, C radians per second get changed on the output. Okay, so if this gives an expression for the instantaneous frequency of the output of the VCO, then I can talk about the instantaneous phase of that signal as the derivative of this instantaneous frequency. And I'm starting to use terms that I hope were introduced in 314, things like instantaneous frequency, instantaneous phase, as being the derivative, the instantaneous frequency being the derivative of the instantaneous phase, and the instantaneous phase being the net angle inside of your sine or cosine. Okay, so then the net angle of V naught is going to be expressible like this, right? As proportional to the linear, to the integral of the input to the VCO. So this block diagram is kind of on a conceptual level. You wouldn't call this you couldn't do a block diagram reduction on this because there's no Laplace transfer functions. In fact, there's quite a few nonlinear things. So if you were to take this as a 302 problem, you'd kind of be stuck, right? Because I told you the very first thing we're doing is phase detector is we're using a multiplier. And we never did any of that in 302 because it's not a linear operation. However, once you make all those analyses that we did on the last slide, you can actually get a reasonable mathematical block diagram to represent it. So this, let's see here. This is what used to be the phase detector. This is what used to be the loop filter. And this is that integral that I showed you coming out of the VCO. So it's not a one-to-one mapping, like not every block here maps to a single block there. I've mixed some things around, but everything on this page has a home on the previous slide. Are there any questions about where all this stuff came from? I'm dubious, but without any input, I think I'll carry on.
Oh, I actually have one question.
Yeah, go ahead.
What does the dot mean inside the sine function?
It means take the sine of the input.
Oh, the input, okay.
Yeah, yeah. Okay, so let's see if we can't, well, okay, I guess the first thing is we also never had any sines of our signals in 302. And that's because taking the sine of a signal is also a nonlinear operation. So if we make this small angle approximation that theta e will only take small values in magnitude, then sine of a small angle is the same as that small angle. And so this sine block becomes a 1, or a pass-through block. And then it becomes a 302 problem. Then it becomes design H such that the closed loop system has desirable features. Okay, so let's make that assumption. Let's start easy, and then we can complicate it later. Story of my life, right? So if we start easy, we should first specify what the input that we're trying to track is, right? What are we trying to lock onto? So let's say that the input isn't coming at the nominal frequency that we thought it was coming at. Let's say that it's coming at some other frequency, omega naught. So even this is a little bit too general, right? So let's do some subcases. So in case 1, let's let the two frequencies match, and let's let the phase offset be a constant. Let's call that V0. So in this case, then the phase of the input wave is going to be in the Laplace domain. So then theta sub I of S is, what do we get here? If I make the simplifying assumption that the frequency that we see is the frequency that we expect, and also that the phase that we see is a constant non-zero offset phase, what would the Laplace transform of the input signal to this block diagram be? Oh, there's a chat. Did I miss the chat? I hope the chat says phi naught over S. No, it does not. Okay, so am I going too fast?
No, just forgot the table transform for the step.
Okay. So from that Laplace table that we've all got memorized, a step in the time domain is a 1 over S in the S domain. And if I scale that step in the time domain, I get to scale it by the same amount in the S domain. Okay. So what else can we kind of immediately see? That if the input is a scaled step, well, what would really help is if I wanted to know about the steady state error, that is theta O of t minus theta I of t as we let time go on. Where I think I've actually swapped the subscripts. I think I want theta I, what I want minus what I have. Yeah, so sorry. I'm going to swap these subscripts. So this is what I want, which is the signal that I'm tracking, minus what I currently have, which is the output of my PLL. All right, so this was the expression for steady state error. So error in steady state. Now, what do I have to know about this system that would allow me to immediately calculate the steady state error given a step input?
Number of integrators in the loop.
Good, number of integrators in the loop. So if I've got a single integrator here that comes from my VCO taking frequency and integrating it to get angle to phase, then as long as I don't have any differentiators in H of S, right, as long as I don't have any zeros at the origin, then this will be a type at least 1 system. So this tells me that my type number is greater than or equal to 1. I say greater than or equal to because H of S might have integrators in it because we actually haven't designed it yet. But certainly if H of S, as long as we're not actively trying to hurt ourselves, as long as H of S doesn't have any differentiators, we'll get at least a type 1 system, which means that we get 0 steady state error to constant offset input phases. So let's talk about a different, I don't want to move past this if you're not following me. So can I get some kind of indication that that made sense? Or even a question if it didn't make sense? All right, 2 thumbs up. And the rest of you are off the page. I can't see you. All right, so let's see how you treat this one. So case 2. We are assuming that we have a frequency offset. So now the frequency that comes in is different than the frequency we're expecting. And I say expecting, like omega c was the quiescent frequency of the VCO, but omega naught is the frequency that we're seeing come into the PLL. And let's say that the phase as a function of time is again a constant. All right, so this is the part that I would like you to help me with. What is the Laplace transform of the input now? I knew 302 was too easy.
Need to find.
So maybe someone can describe the input in the time domain. If you can describe it in the time domain, then maybe I can help us get it into the Laplace domain.
Is it a delay? No, it's not a delay. It's a magnitude based on time. It's a step where the magnitude is changing based on time.
Sure. So yeah, I mean, what you described as a function.
Yeah. Yeah, I guess it's a step function with its I guess with its magnitude based on its slope.
Yeah.
Based on whatever the frequency is, WC minus WO.
Good, good. So we get a jump to phi naught, and then we get a slope of omega c minus omega o per second. Good. So things like a ramp or things like a step plus a ramp, those would be what I'm kind of looking for here. Do you see how if I have this frequency offset, then the phase of the input wave kind of evolves like a ramp? Okay, so the Laplace transform of a pure ramp is just the amplitude or the slope over s squared. How many times can I get the subscripts wrong? We'll play that fun game. So this would be omega c minus omega naught all over s squared, but I'm going to add that to another step. Okay, and so if we have a type 1 system, but we present that system with a ramp input, we're going to get a finite but non-zero steady state error. If, however, we had a type 2 system, that is, if we included an integrator in the loop filter, then the steady state error, even in this case, would be 0. So this case bifurcates into 2 cases. So in a type 1 system, that is, H has no integrators. We get a steady state error. So error steady state of omega c minus omega naught all over A, B, C over 2 times H of 0. Basically the DC gain of the loop filter. Otherwise, if we have, say, a type 2 system, and that would mean H has one integrator, then the error steady state is 0. So this actually gives us, the reason that I harp on this and kind of give you a hard time for not remembering 302 is that it actually serves as a basis for what the loop filter should look like. If you need your PLL to be able to track things that you know will have the same frequency that you want them to, but might have a phase offset. This, for example, would be if you were trying to build a phase shift detector. So if you communicate a 1 bit by a shift in phase of, say, 45 degrees forward, and a 0 bit by a shift in phase 45 degrees backwards, but you know the exact frequency it's going to oscillate at, then case 1 would be actually the only thing you need to design for. Right? You'd only need to track constant phase changes. However, if you were going to do something like, well, frequency shift keying, that is a 1 bit is omega C plus 10 kilohertz and a 0 bit is omega C minus 10 kilohertz, then all of a sudden you have frequency differences that you need to account for. Also possibly phase differences if your 2 local oscillators were started at different times. Okay, so that's more like a case 2, and that's a more complicated design, so you would need a more complicated loop filter. In this case, complicated means adding an integrator. Questions on that?
I have a question about how we differentiated from a type 1 and type 2 of H of S. So I know that we're guaranteed at least a type 1 in this. How, based on H of S, how do we not have no integrators based on and have a type 1 system, or just one, when there's a like an S and an S squared? How does that go to become a no integrator? Oh, because is it based over 0? Is that why?
Well, so let's be careful that we're telling things apart that need to be told apart. The system will have at least one integrator. So here's one. And then if this H of S has more integrators, then we can increase the type number that way. The input is an entity that lives completely separate from the system. And so these S squareds and S to the 1s are characteristic of the input, not of the system.
Okay, that makes sense.
Okay. And the reason I'm being a little coy about this is because we actually haven't specified H of S yet, and I want to try to leave it as general as possible. And I grabbed the low-hanging fruit here, which is the steady state analysis. We haven't done transient analysis or anything like that, which of course, you remember that throwing integrators at your problem helps your steady state performance, but it hurts your transient performance. So no free lunch here.
Thank you.
Quick question. The phase difference doesn't like linearly increase. It goes like up and down, right? Does that mean that the transform stays the same?
I didn't quite catch the question part of the question. Can you say it again?
The transform of the phase just stays as what is written there.
So if the phase can be represented like this in time, then yes, it will be represented like this in Laplace. Now, what I haven't talked about much is like this assumes that there is a notion of t equals 0 because we're talking about a unit step. And so when I talk about something like a phase shift key type communication system, I'm assuming that every time the transmitter, like every bit period, we're resetting time equals 0. And so when I say something about steady state, I want you to take that in the context of a communication system where if I'm sending 1 megabit per second, so 1,000,000 bits per second, I only have a 1 microsecond to decide whether it was a 1 bit or a 0 bit. So therefore, this limit as t goes to infinity if infinity isn't the same as a microsecond, we're in trouble. Yeah, and so if the dynamics of your system are such that it reaches steady state with under 1 microsecond, awesome. But if your dynamics are so slow that steady state takes a millisecond, you've already lost 1,000 bits by the time you're deciding on the first bit. Okay, so I'm not sure that answered your question, but it was a point that I wanted to make in this lecture. that what steady state means is always context dependent.
My question got answered though.
Okay, thanks. It was somewhere in there in that word salad.
Yeah.
Okay, sweet.
I have a question about the second block. What are ABC just concepts from HFS?
So A was the input amplitude, B was the output amplitude, and C was the slope of your VCO.
Okay, gotcha. Thank you.
Mm-hmm. Yeah, I don't think you lose much generality if you let A and B be 1. I'm just saying you could make them different. Okay, so now that we're so comfortable with 302 type subjects, let's kick it up a notch and consider a nonlinear control problem. So this would be something that I don't think you would see until 513. So this is, you know what, I can't make a small angle approximation. I have to deal with a sign inside of my loop. So if I'm going to make that block more complicated, you better believe I'm going to make the other block more simple. So I'm going to assume that my loop filter is just a delta, an impulse. Okay, so again, we're assuming that this is not negligible. But that this all of a sudden is negligible, right? Only one complicated thing at a time. Okay, so if that's true, then what do we have here? We have theta dot, I guess we can start down here. Theta, so I'm talking about this signal. That equals what? The sine of theta E times some gain. Where K, let's let K be ABC over 2. Okay. So if I know the rate of change of the output in the time domain depends on the sign of the error, which is itself a function of time. Like I dropped the theta E of t, but this should be theta E of t. I know that the output is the difference between the error and the input. Right? So if you think about our expression for error, theta in error, if you look at the block diagram, it's the input minus the output. So if I differentiate both sides of this expression, I get the rate of change of the error is the difference between the rate of change of the input phase and the rate of change of the output phase. I guess some notation I'm assuming you're familiar with is that the dot means a time derivative. Okay, I'll get that in writing. Okay, so if I rearrange this for theta O dot, I get theta E dot minus SI of t, and I can move that over and get this expression here. So I'm looking here now. So what I've got is, let's see, where do I want to go with this? Well, I think that what we have here is an expression for kind of a dependent variable as an offset and a sinusoid, which is a function of theta e. Okay, so if theta I dot is a constant, then I can express theta E dot and theta E like the graph here on the right. Does anyone have a question about why I can, like, this is just an offset sine wave then, with quote unquote DC offset given by theta I dot. Okay. So in its most basic form, and we're doing nonlinear control in a class that is not about nonlinear control, but in its most basic form, this is a relationship between the change of a quantity and a quantity, right? This is kind of like a what do you call it, a vector field, or in really it's a state space representation. So let me walk you through what's going on here. Given an error, a theta error, I can calculate the change in theta error given with this plot. Right? So you tell me that the theta error is this number. I look up and I see that the rate of change of theta error is a positive number. So what does that tell me? That at the next, quote unquote, next time instance, what is theta error going to be? Larger or smaller than what it just was?
Larger.
Good. So at this point, we get pushed that way along the curve. So, okay, let's say at the next snapshot, we're over here. And this tells me that the rate of change of theta E is positive again, which means we get pushed this way again. Now, what happens if we end up here? Well, this tells me that the rate of change of the error is negative, which means which direction are we pushed? Back that way. Okay, so this is fundamental to nonlinear control, but it is hard to grasp the first time you see it. And that is, if I have a function of the change of a variable in terms of the variable, then I get to know where that variable will go at any given time, what direction it'll be pushed. So this tells me if I'm right here at that intersection point, the rate of change of theta E is 0, which means the next theta E is the same theta E, which has 0 rate of change, which means the next theta E is the same theta E, which has 0 rate of change, which means this is what we call an equilibrium. Yeah, that's right. It's an equilibrium point. If the error ever ends up at this point, it won't change. Now, I'll know that you're with me. Well, I'll know that someone is with me if you can tell me, is this a stable or an unstable equilibrium?
Unstable.
Was that an unstable?
Yeah.
Tell me why.
Because
please.
Because theta E is not 0. So if it's not changing and theta E is not 0, then, oh, actually, I don't know. On the right track?
Your reasoning got you to start thinking on the right track. Your original answer was incorrect, however. Don't think about stable versus stable equilibria as being 0. Think of what would happen if you nudge the state out of the equilibrium. Does it want to come back or does it fly away?
So I'm assuming, I guess, the equilibrium stays at a state, a stable, as a constant number compared to an unstable one going to infinity. And if it's but that would wouldn't that have to be that it's increasing and decreasing at the same amount? The rate of change is increasing and decreasing the same amount, or is that different too?
So the magnitude isn't really as important as the sign.
Okay.
So if I start at this point and I nudge the state that way, where does the system nudge the state after that? So I'm doing the first nudge, and the system is doing the next nudge. Which direction does the system nudge it?
Right.
Right.
It's just going to oscillate, right? Because the integrator is trying to correct the error.
Yeah,
like
that's
one way or the other, and then it's just going to like oscillate around that point.
That's another way to think about it. I think that when we get to my next example point, that reasoning might be a little thrown off, but yeah, if I nudge it left, the system nudges it right. It might overshoot, in which case if it overshoots, it'll get nudged back and it will oscillate and it should settle back down here. So this is, because of that rationale, this is a stable equilibrium point. Right, the actual definition of stability, and we learned about it by like poles on the left-hand side or right-hand side, but that is only applicable to linear time invariant systems. The fundamental definition of stability is, does a perturbation return to the state or does it go to a different state? Okay, so I promised you something different if we go to a different part of the sine wave, but I want to make sure that everyone understands that argument.
I have a quick question, I guess. So
sure.
Based on this graph, it's saying that the rate of the error changes based on where the error is, or what
exactly
the error is.
Yeah.
I mean, obviously it would push down based on this graph, but isn't that positive? And like nominally, wouldn't that be a positive rate going away, or maybe, positively above from the air, or from the air, I guess. I don't know how to explain it, I guess, necessarily, but it's like maybe because it's not based on time or another kind of
right thing. So there's no time anywhere in this graph, right? This is a quantity, the rate of change of a quantity plotted versus that quantity. And all I'm doing really is asking you, is the rate of change positive or negative?
Oh, okay.
So let's try another experiment. Let's start here at this intersection point. Now, if we start there, if the state, I'm using state and theta E interchangeably. Those are the same thing in this case. If the error starts there, where does it go next?
Oh, it doesn't go anywhere.
Because the rate of change is 0.
Rate of change is 0.
Okay. So this is another equilibrium point. That if I start there, I stay there. Now, what if I nudge the state from an equilibrium point and I nudge it, say, to the right?
It'll go to the next equilibrium point.
That's right. The system continues that nudge and pushes it away. Okay, so this is an unstable equilibrium point. Okay, in linear systems, we didn't have any of this. The systems were either stable or unstable. But in nonlinear systems, you can have multiple equilibria, some of which are naughty, some of which are stable. Okay, so, and the same argument applies down here. If I nudge the error smaller, then the system makes that smaller error smaller, which actually nudges us in the quote-unquote correct direction, because where do we want to be? Where do we want to be on this graph? Where is the best state for us?
Closest to 0, I'm assuming.
Yeah, we want no error. So we want to live here. But this particular system does not abide that, because if we're there, this is going to push us, well, a positive. So it's going to push us this way. And so let me make sure that we get everything written down that we've established. This guy is unstable. It's still an equilibrium, but it's an unstable equilibrium. And then this is the point that I actually want to pay attention to. This is, it's an equilibrium. Now you tell me, is it stable or unstable?
Stable.
Yeah. So we get pushed, from either direction, we get pushed towards it. So this is the best, that's a big B, is best equilibrium. And I say best, not because it's stable, like that's a bonus. It didn't have to be, but it's best because it gives us the theta error in steady state is the smallest. Right, so in this case, for this particular PLL, the error in steady state, provided we start in kind of this range, provided we start with an error in that range, the steady state error will converge to this point. Now, why did I pick those 2 points, the left and right points? Well, if we started here, we just said we're going to get pushed away. If we started here, we're going to get pushed away. And so this system, given its current form, can handle initial errors that live anywhere between here and here, and it will push them to a steady state error right there.
So does this graph represent multiple systems based on the parameters that we've created, or does it only a particular system, one system itself?
We made a couple of assumptions. We assumed that the loop filter was not doing anything for us. And we also assumed that the rate of change of the input phase was a constant. If either of those things are not true, this becomes significantly harder.
Okay, but there are multiple systems based on that parameter, and this graph represents those systems and where the errors could fall under based on our parameters that we've set already.
I think that this only represents a single system. This is a system whose a nonlinear system who takes a sign of an error and then passes it through a gain. So for that particular system, we get a behavior that's encapsulated in this graph, assuming the input rate of change is constant. If you were to change this, if you were to say h of s had a second integrator in it, then all of a sudden we would have a second order system and we would need more dimensions and we'd have things coming out of the page and all that other craziness.
Oh, okay, I see. I think based on the system, but the errors, I see now, we've always said, well, like you said, in linear time invariant systems, there's only one really, like, oh, there's only a constant error. In this one, there's differentiating errors based on a single system, right? And so that's where we get this on our particular. Okay, yes. That makes
so. Yeah, the other salient difference between this problem and an LTI problem is that the final state of the system or the steady state value of the error depends on where you started.
Okay.
And that's not true in LTI systems. LTI systems, if your system is stable, all roads lead to that point.
Okay.
Here, the system is sometimes one, sometimes the other, and which equilibrium you end up in depends on where you start.
Okay, that makes sense.
So if this is your kind of thing, I encourage you to take EE416, and I think 514 probably extends upon this later. But we are out of time today. I will see you Wednesday.